All right. What's this form of an equation called?
Slope-intercept form.
Slope-intercept form. Do you know why they call it slope-intercept form?
Because it's where the intercept of the slope.
It shows the intercept and the slope. Okay, pretty straightforward, right? We got our slope-intercept form of a linear equation. Okay. In context, what does y typically represent? What are some examples of what y could represent in a context? It's the dependent variable. Okay, what else? What else could it be? We had some examples yesterday. More specifically. You're thinking a different part for the starting number. You're thinking a different value. What are some examples of what y could represent in context? Yeah, but in context.
What's the first letter?
There is none. There's a bunch of different answers.
Y could just be like I said the base.
The goal, the final, the total, okay? All of these things are dependent upon the input, okay? So y, yes, it's our dependent variable, not independent. Meaning the value of y depends on whatever x is. It's our dependent variable, typically represents a total or a final amount or a specific amount in time. A very specific amount at some interval of whatever x is, okay? But generally think of like a total or a final or a goal or a result, okay? Y is the output of the equation, all right? It is our output. What is m?
The variable. Independent variable. No.
It's a constant something. What is m?
No.
What is m? What is m? What is the m? What is the m in our slope-intercept form? The slope. It's the slope, guys. Come on. M is our slope, also known as our constant rate of change, okay? And that is so very important because another thing we're going to cover in a future unit is the difference between a constant rate of change and a non-constant rate of change in comparing different types of equations with constant versus non-constant rate of change. Then x is our, what is x? It's our independent variable. If y is our output, x is our input, okay? So our independent variable, our input value, okay? And that's going to be whatever interval is changing along with the constant rate of change, okay? The constant rate of change tells us how much to change by. The input tells us how many times to do it, how many times to change. And then what does b represent? The y-intercept, the initial point. Help if I could spell. Y-intercept, the initial or the starting point, okay? So if we are in slope-intercept, that's typically what those values represent, okay, in a context. But not every context is modeled easily by y-intercept form of an equation. The other type of equation that we have is our standard form. Standard form. And this is most useful when we're comparing quantities. Okay? Typically when we're comparing two quantities or there's a direct relationship between two distinct quantities, they give us two variables, we're typically then going to use the standard form to describe that relationship between those two quantities. When we often have two input values, in a sense, we're looking then at the standard form of the equation. And so we'll have quantity 1, so quantity 1, and then whatever quantity 2 is, and then C represents a total or a final amount or a combined amount. Okay, that's what the standard form, the standard model is used for. So being able to kind of represent either one of those based on whatever the context is describing. So like I said yesterday, most of the problems on the SAT will be based within context. So we're going to be taking a look at a few different in-context problems. And again, for a lot of these, there's multiple ways to approach the problem. We'll kind of talk about some of the options and see if we can identify any patterns or trends that will make the process easier overall. So we have a table here that's representing the relationship between merchandise weight in pounds and shipping charge. Okay, so they tell us to write a function in slope-intercept, so we know we want y equals mx plus b, that relates y, the shipping charge, to x, the merchandise weight. So they're telling us, here's our x value, here's our y value. Okay, so we're writing a model in terms of x and y that represents this linear relationship. Okay, so what is the first thing that we can find by using this table so that we can get our model? The slope. Okay, y is just all these values plus an infinite number of more. Okay, x is all these values plus an infinite number more. X and y are just part of the model. But using those, the first thing that we can do is we can find our slope. How do we find slope? That'll give us a ratio of charge to weight, but it's not going to give us the rate of change. And the emphasis there is change. Okay, so you're on the right track. It does have to do with the ratio of y over x, but more specifically, it's the amount of change in y divided by the amount of change in x. Okay, so how do I find the amount of change from one y value to the next? Subtract them, right? We subtract two of the y values. So it doesn't matter which two we use, we just have to be consistent. I'm going to use the smaller numbers because smaller numbers. So I can find the difference between two of the y values. And then what about the x? What about the x? 10 minus 5. I got to make sure I'm using the corresponding. If I got 2390, I need to use 10. I got 1649, I used 5. So I can subtract these. So I get 750 over 5. Okay, we'll simplify that in a second, but I want to take a moment to say and ask, what does this ratio specifically represent? What is it telling us about the scenario specifically? Okay, that's very general, and that's correct, but I want to be more specific. So using what do the variables represent? What does y represent? Our y is 7.5. What is y modeling? The charge. What is x modeling? Okay. Okay, so remember, which one's dependent? Or sorry, let me rephrase that. Which one's independent, the x or the y? The x. So we're determining the x, right? So as the weight increases by 5, the cost increases by 750. Okay, that is what the slope is modeling. As the weight increases by 5 pounds, the cost increases by $7.50. And then we can reduce this down to a unit rate as well, which we'll do in a second. This isn't saying that 5 pounds will cost $7.50. This is saying that as we increase the weight by 5 pounds, the cost will increase by 750. There's an initial point, okay? This isn't giving us a specific point. This is giving us a change from one point to the next, okay? So it's going to increase by 750 every 5 pounds, right? Okay, let's find the unit rate. How much is it increasing every pound? How would I figure out how much this is increasing by every pound? Divide 7.5 by 5, okay? So we get a slope of 1.5. So as the price or as the weight increases per pound, the cost increases by 1.5, $1.50, okay? So now we've got part of our model. We found our slope, okay? So far we got y equals 1.5x plus some starting amount. That is an excellent way to approach it, okay? There's a couple different ways, and we'll go into more detail tomorrow about other ways to kind of find these missing values given some points. But again, we want to look for patterns. If we know that our cost goes up by 750 every 5 pounds, and we have the cost after 5 pounds, if we take away that increase from the 5 pounds, that gives us the cost at 0 pounds. Because if I subtract 5 pounds from 5, I get 0 pounds. And if I subtract the 750 from the 1649, I get $8.99, the initial cost. Okay, that gives us the initial cost of $8.99. Now we can then fill in for our model. And there's our model that we can now use to predict any cost based on weight. I want to ship a package that's 12 pounds. I plug it in for X, and now I know the cost for 12 pounds. If I want to know it for 37 pounds, I plug in 37, and now I know the cost for 37 pounds. Does that make sense? Okay, so there's our model. That was slope-intercept. Next one is a model that's in standard form. We see we have a quantity with X plus a quantity Y equals sum total. AX plus BY equals C, which again represents our total. So we see that we're comparing these two quantities just based off of the equation. Here we have a mixture problem where they describe it. What is it we're trying to find in this scenario? Okay, which variable is that going to be? We're trying to solve for X, right? We want to figure out what X is. And I've got X in here twice. Well, in order to solve for X, I have to know something about Y. What do I know about Y? It's 20%, but I need a value for it because that's what this is representing. This right here, that's 20%. I've got 10% of whatever this volume is. I've got 20% of whatever this volume is. I want 12% of their combined volume. So what do they tell me about Y? I need a value for Y. 100 milliliters. If Lawrence uses 100 milliliters of 20%, how many milliliters of 10% does he need? So they're telling us what Y equals with 100, and then we can use that to solve for X. What can I do to make this equation easier to deal with? Because these decimals get annoying. Multiply by why 100? It's percentages, right? Multiply by 100, we got 2 decimal points. That'll clear up my decimals. So I'm going to have 10x plus 20y equals 12x plus y. Simplified our equation. Now we can substitute in. We're going to have much easier math to deal with. So we've got x is what we're solving for. 20 times 100, 12x plus 100. Now what? Okay? So X equals 400 milliliters. So if he uses 100% or 100 milliliters of the 20, he needs 400 milliliters of the 10. Now, this is also a really useful question because sometimes they'll give you this scenario and they'll ask for an equation and they'll give you like options. This is the general structure for any type of mixture problem. Whether you're mixing a percent, whether you're mixing a cost, whether you're mixing where X and Y represent a volume or a mass, okay, some measurement quantity, and then the coefficients are either a cost or a percentage. It's this general structure where we have quantity A plus quantity B equals, and then whatever the final is, and we're adding the two quantities together. What is the total amount? It's this same general structure every time. All right. Given this scenario, which of these would most likely be the correct interpretation for the y-intercept? Say again. The setup fee of 550. How do you know? Yeah. Yep, perfect. X represents months. The y-intercept is when X equals 0. So at 0 months, you've had 0 service. They showed up to your house and they installed it. Okay, they hooked up the cables, but they still charged you before you got anything. That's the initial cost at time 0. Which of these is the most likely option to represent the slope? Total represents slope. The monthly charge of 35. This would be a y value. This would be a specific value because we've got total. Okay, so this is after 1 month of service. How much did I pay? So that's not a slope. Monthly charge, we've got a monthly charge of 35 or a monthly charge of 550. Well, the 550 was the setup fee. So this would represent slope. Farm purchased a combine harvester valued at $330,000. The value of the machine depreciates by the same amount each year, so after 10 years, the value will be $80,000. Which of the following equations gives the value V of the harvester in dollars T years after it was purchased? Right off the bat, we can eliminate one of these options. Why?
They don't stay in. Wait, no.
See? Why?
No, wait, sorry.
Why?
Because you can't, if the value depreciates over time.
It's not going up, right? This means we're going to have a negative slope. Depreciates, goes down. Appreciates, goes up. Okay, depreciates, decreases. This is a positive slope, so we can eliminate that option. Okay, we can also eliminate another one. Why D?
Because that's after the 80,000.
Okay, so that's the final amount, not the rate of change.
And if you plug in the 10, I think
Why?
because you're not subtracting the already depreciated value.
Yeah, this represents our initial amount, right? So these two have the same rate of change, but this is the final amount, not the initial. So we can eliminate that one. So my question is, where did 25,000 come from?
Because that's how much it depreciates.
How could we find that? How could we find the amount that it depreciates each year?
You divide 80,000 from 10 and then subtract.
You've got the right operations, but in the wrong order. So pause for a second and think about it. You're so close, but you got it a little jumbled up. Okay, so we take our initial amount and subtract our final amount. So the change in the y values, the change in the cost, divided by the change in the time from 0 to 10. The difference, okay, from 0 to 10, So then we're going to get a rate of change of $25,000 per year. $25,000 per year. Actually, this should be opposite because it's negative 0 minus 10 and then negative 25,000. There we go. Okay, so that's how we can determine what our options are. Questions, comments, concerns, queries, conundrums? All right, we're done. You have